Hello friends, welcome to Susan and John Math Tube. Today we are going to learn about probability distribution functions in a continuous scale. Last time, in the last two videos, we learned about probability distribution functions, but everything was measured in a discrete scale. So, the first question is, what do you mean by continuous function, or what is the or why do we need continuous functions? Okay, let's start by discussing a very simple question but a very important question. Can any one of you list all the numbers between 1 and 2? It sounds simple, it might sound a little bit silly, but it is a very important question. Can you list all the numbers between 1 and 2 in a continuous scale? Or can you tell me all the numbers between 1 and 2? I mean real numbers, not integers. Maybe you'll be able to list the integers between any two numbers, not 1 and 2. There are no integers between 1 and 2. Okay, the answer is no one can ever list all the numbers between any two real numbers. So, listing all the numbers between 1 and 2 is practically impossible. So, what mathematicians do is they use two symbols, and I'm sure you learned this symbol in your high school classes. One is called the open interval and the other is called the closed interval. So, if I want to tell someone that I'm using all the numbers between 1 and 2, I'll write like 1 comma 2. And what does it imply? It implies I'm using all the numbers between 1 and 2 excluding 1 as well as 2. At the same time, if I use square brackets, then it means I'm using all the numbers between 1 and 2 including 1 and 2. Okay, or you can use this. Let's say x is our required number, and you can write 1 less than x less than 2. And for the second one, you can write 1 less than or equal to x less than or equal to 2. That means the number I am using is between 1 and 2, exclusive here and inclusive over here. So now we know how to list all the numbers between 1 and 2. No, we cannot list, but still we have a notation. So now I want you to focus on this example. The time taken by athletes to complete a 100-meter sprint. Think about it. Okay, so what's the answer? Will you get the same answer or will you get different answers? I'm sure we'll get different answers. Okay, but all the answers will be between some numbers, like it will be between two numbers. Let's say 8 seconds to 15 seconds. I'm not sure about the correct answer, but let's guess. Let's say it takes somewhere between 8 seconds and 15 seconds. So this is an example where we measure in a continuous scale. Look at this. We are not able to tell the exact answer, but we are able to give an interval. Okay, I'll give you one more example where we use the continuous scale, that is the mileage of a particular vehicle. I'm sure most of you have vehicles, and now I want you to imagine how much kilometers you can travel in 1 liter of fuel. Is it a constant or does it keep on changing according to road conditions and driving conditions. Of course, it will change. You'll never get the same mileage, but I'm sure you'll be able to give me an interval. Maybe some of you will say you can travel 10 kilometers to 20 kilometers um, per liter of fuel. Some others may say maybe 12 kilometers to 15 kilometers. Some might say 20 to 25. Anyway, I'm sure about one thing. You'll not be able to give me an exact answer, but you'll give me an interval. And the answer will be somewhere between those two numbers. So that's it. Another example where we use or we measure in a continuous manner. Okay, now the last one. You can imagine lots of examples like this. Anyway, I'll give you one more example. How much water do you consume every day? I mean, till the last drop. Don't give me answers like 8 liters, 4 liters, 2 liters, or 100 liters. No, not like that. I want the exact amount till the last drop you use every day. See? You won't be able to give me the exact answer. So, again, your answer will be between two numbers. That is, we are measuring in a continuous manner. Okay, so let's move ahead. Like we discussed in the last two videos, in continuous probability distributions, we have random variables. But the only difference is our continuous random variable can take continuous values. That means in most of the cases it will be an interval. It can take infinite number of values, not like our discrete, not countable values, but infinite number of values. So in most of the cases it will be in intervals. And another important thing, if you watch the first video in probability distribution, you will notice that discrete probability distributions can be listed, or we can write with the help of tables and diagrams. But in the continuous probability distribution, that is impossible. So don't expect a tabular form over here. Okay, that is, do you remember the input values in our discrete probability distribution? Yeah, we call them xi's. Xi in the sense x1, x2, x3, x4, etc., etc., etc. But in the continuous case, this is impossible because there will be infinite number of values in the interval that you cannot list. So we use x. We just use x, where x can be any number, any real number in the given interval. So I hope you're okay with the point. Now, again, I want you to remember the discrete case. In the discrete case, our input values will be x1, x2, x3, or in general xi, and the output is of course probability values. That's what I told you earlier. Probability function means the input will be related to the random experiment and the output will be related to the probability of this particular value. Anyway, in continuous, we have our inputs as x, where x is any number in the interval, and the output or the probabilities will be given by the function values. Okay, now that is something very interesting and very important. So this function generates probability values for each and every input, but probability values are never negative. Probability always lies between 0 and 1. So that implies the output values of our probability density function in the continuous case will always remain between 0 and 1. Did you get the point? That is, these values can never ever be negative. So look at this. The probability is given by f of x, where x is our input and f of x is the output. And the output is nothing but probability value. And since they are probability values, they are non-negative. Make it very clear, the values can never ever be negative. The input can be negative, but the output can never be negative because the outputs are the probability values. So this is our first observation. You input any x in the interval, you're going to get something bigger than or equal to 0. Now let's think about the coordinate x comma f of x. I'll repeat, x is our input and f of x is our output. So this coordinate will always stay above the x-axis. Did you get that? This coordinate is always above the x-axis. Or the graph of our probability density function should stay above the x-axis. Okay, I'm sure some of you who are watching this video are not that good in functions. Or maybe some of you are not that good in integration. No, I'm not talking about the problem solving techniques. I'm talking about the concepts, the graphs, what is integration, etc. So for the next few minutes, we will be discussing some basic things in mathematics, that is our integrals and functions. So let's move ahead. So I'm going to borrow a few things from mathematics, and it starts with the story of our integration. So tell me, what is integration? Think about it. What is integration? Integration is nothing but summation. So what is integration? Integration is nothing but summation. And if you want to make it short, it's just a long S, which represents summation. And not any summation, but continuous summation. So you might be wondering, what's the difference between summation and continuous summation? So take a look at sigma n is equal to 1 to 5 n square. This sigma stands for discrete summation, not continuous summation. So all I have to do is I have to input the value n is equal to 1, so that I get 1 square and sigma says addition. Then I'll get 2 square plus 3 square plus 4 square plus 5 square. So this is discrete summation. Now imagine the situation where you add x square using all the numbers between 1 and let's say 5. Okay, this is where we need integration. So integration is not just any summation, but what sort of summation? Continuous summation. Okay, and just a small note, if you are interested you can read. Yeah, it was from the great mathematician Leibniz, who introduced some beautiful notations in mathematics like d by dx, the integral symbol, etc. Anyway, let's move ahead and let's check out the affair between Mr. Integral and functions. So let's start with the function, and I'm sure you know how to represent a function y equal to f of x. And when you represent a function like this, it means the input value is x and the output value is f of x. So for every input we have an output, and that input comma output creates a coordinate. And this coordinate can be represented as a point in our xy plane. That means every function corresponds to a graph. And I want you to notice one more thing. If your input value is x, then the height at that point will be f of x. If your input value is x, the height at that point will be f of x, and hence this coordinate will be x comma f of x. Okay, to understand the affair between integrals and functions, let's analyze the function y is equal to x square. I'm sure the students from math background know very well this graph. The graph of this function will be a parabola. But let's analyze it. If I input 0, I'm sure I'll get the output 0 square, that is 0. If I input 1, I'm going to get 1. If I input minus 1, I'm going to get minus 1 the whole square, that is 1. And etc, etc, etc. And if I try to graph it, I get a parabola. So you can see corresponding to each and every input. I think you're able to see those numbers. Input is 0.36, 0.37, and you're getting corresponding output values, and that generates the graph. So I hope you're able to visualize every function corresponds to a graph. Now, take a look at this. It will be more clear. So at 0, the output is 0 square, and are you able to see the values? For every input there is an output, and input comma output will be that pink curve, and we call that curve a parabola. Let's move ahead. So take a look at this integral 1 to 2 x square dx, and we have our function y equal to x square, and I'm interested from 1 to 2. As I told you before, integration stands for continuous summation. Summation means addition. And what are we going to add? These quantities. That is, I'm going to add 1 square into the differential at that point, then 1 point the next square, etc, etc, etc. So let's try to visualize it. And for that, I will draw one line which, if you want, you can call it a rectangle. Let's say this point is x. As I told you before, what is the height here? F of x. But what is the function? X square. I showed you at 1 the height is 1 square. At 2 the height is 2 square. At 1.5 the height will be 1.5 square. So in general, if I have a point x, then the height will be x square. So the height of this red rectangle, which is a line, you have to imagine that's a line. So we can visualize this to be a rectangle with height x square, and let's say this part is dx. So the height is x square and this length is dx. So x square into dx is actually the area of this red rectangle. So look at this. We are going to add from 1 to 2 all the rectangles. Just imagine, I can create many rectangles like this. I'll repeat. I can create many rectangles like this. So now you tell me, if I add all those areas, what am I going to get? Exactly, I'll get the area under the curve above the x-axis and between 1 and 2. So I'll end up with the area between 1 and 2. Okay, now one very important thing. Do not get misguided, because integration is just continuous summation and it need not give the area. Okay, now some of you might be wondering, just a minute back I told you integration gives area. And here I am warning you, integration may not give us an area. So, take a look at this. If you integrate the function sin x into dx between 0 and pi, you're going to get the answer 0. But does it mean that there is no area between 0 and 2 pi under or above the graph of sin x? No. So, once more, I want you to read this. So, integration is just continuous summation and it need not give us the area. So, let's go for the graph. So, you can see the graph of sin x between 0 and 2 pi. And I think you understood why we are getting the answer 0. Look at the height of the graph at pi by 2. It is 1. And what is the value at 3 pi by 2? It is minus 1. When you add 1 and minus 1, we get 0. Likewise, if I add it over here and here, it is, I guess it's like 1 by root 2 and minus 1 by root 2. Likewise, for every height, you can see a depth. For every height, you can see a depth. So the total sum will be equal to 0. So my friends, don't get misguided because integration is just continuous summation and need not give us the area. Okay, now there is some good news. The good news is, do you remember the example 1 to 2 x squared dx? And you saw that we were able to find the area. But when we tried 0 to 2 pi sin x dx, we got the answer 0. It's not the area. The area is actually 4 units. You can calculate it. The answer is actually, the area is actually 4 units. So, we have some good news. The good news is, if the graph of a function is completely above the x-axis, then integration gives us the area. So, now let's move back to our probability. So, with this good news, this part is going to make sense. So, we start with the statement, probability values in continuous probability distributions will be the function values. But probability values are non-negative. That means x comma f of x is always above the x-axis. So what I'm trying to conclude is, the graph of any probability distribution function will be above the x-axis. The graph of any probability distribution function will be always above the x-axis. And one more very important thing, if you integrate from a to b a function which is positive, of course, you're going to get the area. So remember, integration is continuous summation, but if the function or the integrand is positive for each and every input, then the integral will be the area. So I'll give you a few examples, and before that I want you to take a good look at the graph of e to the power minus x. You know that e to the power infinity tends to infinity, and e to the power 0 is equal to 1, and e to the power minus infinity tends to 0. So when we input negative values, the power becomes positive, because if I input minus 1, it will become e to the power 1. When I input minus 5, it becomes e to the power 5. So the negative side shoots up to infinity. At the same time, the positive side, it becomes asymptotic to the x-axis. Now I'll give you an example of a probability function. See, this is a probability function. Look at the graph. As I promised, the graph stays above the x-axis. I mean, including the x-axis. So, here goes our e power minus x for positive inputs. So, you can see that we are considering this part of the graph. And if you have any negative input, the answer is 0. So, this is our graph. I'll give you one more graph. It's another probability function, and as I promised, the graph stays above the x-axis, of course including the x-axis. So look at this. For any negative input, the value is 0. See, the probability values are 0 till here, and then a parabola, and finally 0. Okay, now one more very important thing. In discrete, we had discrete summation. That is our sigma. In continuous, we will use continuous summation, and that is our integral. So, the properties in discrete probability distribution can be changed into properties for our continuous probability distribution. So, take a look at this. Sigma will become integral, and our pi values, the probability outputs, are nothing but our function values, and the sum of all the probability values is equal to 1. Same thing, the continuous summation of all the probability values is equal to 1. So let's go for the last part, observations. So what's the first observation? Probability values are nothing but the output values of our probability function. But probability can never be negative, so all these outputs are going to be positive. And the last one, if you add all the probability values, don't forget addition means continuous addition, and continuous addition is nothing but our integral. So if you add all the probability values, then we are going to get 1. Now the last and the most important thing, and I hope you still remember the good news. The good news is, if the graph of f of x is completely above the x-axis, of course our graph is above the x-axis, then integration gives us the area under the graph. So what does the last property imply? It implies for any probability distribution function, the continuous case, area under the curve will be equal to 1 unit. So I'll repeat some tips and tricks. Sigma becomes integral, xi will change into x, and pi becomes f of x. So the formula for expectation. Can you guess what will be the formula for expectation in continuous? Of course, sigma will change into integral, xi will become x, and our pi's will become f of x. So what about variance? You can use the same trick. The trick is over here. And how can we forget our standard deviation? What is standard deviation? Yeah, exactly, root under variance. Anyway, I'm going to conclude this video here. So if you want us to make any videos in any particular topic in mathematics, just email us at sjmathtube@gmail.com. And if you have any doubts or any questions regarding these topics, you can email us at sjmathtube@gmail.com. And in the next video, we'll be discussing some problems related to continuous probability distribution function. So till then, goodbye.